Hi folks, Vipin here. Wish me luck. This is my first video on physics theory. I decided to do a topic about Gauss law and the applications of this. The formula that is there in the applications is what is important. So I'll mostly be discussing about the formula rather than in fact arriving at, okay, how did we actually get into this formula? Okay. Now, firstly, let me first tell you about Carl Friedrich Gauss. Pretty lengthy name. Usually, people with lengthy names in olden days are the Germans. So, Gauss, in fact, was a German. He lived from 1777 till about 1855. Now, remember, in those days, living so long was really, really unusual. But Gauss was, in fact, one of the lucky people who could actually live a long and a fairly healthy life. Now, Gauss has made a large contribution to a variety of fields. Electrostatics is just one of them. He's made contributions to statistics, he's made contributions to astronomy, he's made contributions to number theory. Uh, Gauss was a bit of an eccentric. In fact, there is a very famous anecdote wherein his servant comes to him and tells him that his wife is dying, and Gauss replies, "Tell her to wait, I need to finish this problem." So you can imagine how much of an eccentric and a workaholic Gauss really was. So his major contribution in electrostatics would be the Gauss law, as you would call it. So what does the Gauss law actually say? It says the net flux inside a closed surface, the net flux inside a closed surface is equal to the intensity of the charge or the net charge which is there inside the surface. Net charge inside the surface. So this is something that he brought along. Now, let's try and understand what flux actually is. Now, there are two concepts here, electric field and flux, electric flux. Now, electric field happens to be a scalar quantity. Flux, on the other hand, happens to be a vector quantity. Okay. Now, what is the difference, you might ask, between, say, a scalar quantity here and a vector quantity? Now, in order to understand the difference, just look at it as something like this. Okay. When you talk about an electric field is actually something which is static. Okay. You can say that there is an electric field on this surface. Okay. And electric flux, on the other hand, is the intensity or the number of lines, in fact, that are flowing through this field. The more number of lines that are there in the field, the greater is the electric flux. Electric field, on the other hand, is more or less stationary. But flux, on the other hand, is a vector quantity. I hope you understood the difference, because that's the best explanation that I could come across from the research that I did on the internet. Now, let's look at the applications of the Gauss law. Okay, the first application that you come across would be the Gauss law being applied to an infinitely long wire, or you could call it as a rod. I wouldn't recommend rod because a lot of people giggle when they read this term. But nonetheless, let's look at how Gauss law actually applies to an infinitely long rod. I've seen a lot of complicated explanations that are there in the textbook. This is the simplest that I could come across from my research. Now, let's say you have a wire that is here, and the wire has got many charges. Now, because of the presence of a charge, there is an electric field. Okay, at this particular point, you have an electric field. Now, the electric field is a distance of r. Okay, and the length of the wire here you could consider to be L. Now, I will tell you why this actually doesn't become valid in some time. There's one more constant that you need to remember here, that would be this particular symbol. This is what you would refer to as lambda. Now, lambda here is in fact considered as the net charge density, the charge density on this wire that you have here. If you're a fan of Half-Life, let's just make it a circle here. And it's my tribute to Half-Life. So lambda here would be in fact the charge density. So what do you do next here? Now imagine the wire as a cylinder. In fact, it is a cylinder. If you actually look at any wire, although no matter how thin it is, the very design of a wire is in fact that of a cylinder. Okay, you have this is how a wire is actually designed. Now, because it's actually a cylinder, this makes our calculations so much more easier. Now, the flux through the Gaussian surface is equal to the flux through the cylindrical part. This is the cylindrical part that you have here. Now, the flux through the cylindrical part is actually equal to 2 pi r L. However, this doesn't really make sense. One of the reasons I say it doesn't really make sense is because if you go back to this, it says infinitely long. So if I were to use any formula here, let's say I consider the radius of the wire to be 10 centimeters, that's 0.1 meter. I would be in fact multiplying this as something like 2 into 3.14 multiplied by 0.1 multiplied by infinity. The length of the wire here is in fact infinite. So when I do something like this, my value in fact is, I have no idea. So this is why when you want to calculate the electric field here, you actually use this. The surface charge density divided by 2 pi permittivity of free space and R. The whole L here is in fact deleted altogether because it's not really possible to calculate the length of any object which is infinitely long. Once again, I may have mentioned in some of my videos, if you want to understand the concept of infinity, go to the YouTube channel which is known as Number File. Here they've explained the many variants of infinity, and it really gives you a different angle to the whole thing. Okay, so this is one way in fact you can understand the Gauss law which has been applied to an infinitely long wire or an infinitely long rod. Okay, so moving on. Gauss law being applied to an infinitely large plane surface. So a plane surface here. Now this is where it gets a little bit more tricky. Because it's a plane surface and because it's infinitely long, the whole idea of imagining this gets very complicated. In fact, this is something which I would tell any student who's studying science. You need really, really good imagination if you want to understand these concepts. Otherwise, it makes studying really, really difficult. In fact, when I read through your textbook, I found half the concepts here very, very difficult to understand. But if you actually open up your imagination, the whole thing becomes so much more easier. So imagine something which is infinitely large. Now, if you are a bit of a realist, an object which is infinitely large here would be the universe itself. Considering it's ever expanding, that's the best example that I could say that actually fits to something like which is infinitely large, which is an infinitely large plane surface. So, for an object which is infinitely large, you consider sigma, small sigma, as the charge density. Okay, you consider the charge density as sigma. The next thing that you would actually apply here would be this. An electric field on a plane surface is perpendicular to the surface. Now here, this is the area of the surface, and this is where the electric field actually goes on. That is, if I were to take this from a lateral point of view, this is the surface. We'll assume it's a little thick. So this is in fact the surface, and this is where the electric field is actually going. Okay. Now this makes your calculations quite easy. Because it's a plane surface and because a plane surface is really hard to define, I've defined it with a square. So the electric field here is actually equal to the charge density divided by 2 permittivity of free space. So if you are a person who has an inquisitive mind, you would go about asking, how did I get 2 here? Well, it's quite simple. The electric field doesn't just happen in one direction, it happens in 2 directions. The plane surface, although is infinitely long, has 2 sides. We'll call this as side A and side B. Because it has 2 sides, I in fact get the calculation here as 2. Okay. Now, coming to the last application of Gauss law. Now, a Gauss law being applied to a uniform spherical shell. They say shell here because it is hollow. Okay, it's a spherical shell and therefore it is hollow. Let me just pull up a weight here. Not bad. And now what this actually says is you have charges which are there all over this surface. Okay, I'll just do it till here because I have no patience to take it all the way there. Now, wherever the charges are present, you have an electric field. So, what is the electric field on a uniform spherical shell? Now, the electric field here would be from the center to here, the radius. Now, if you're able to know the data, wherein you are able to know the radius, you are able to find out the total amount of electric field intensity on this particular sphere. Okay, and of course the value of the charge that is in fact present all over the sphere. So how do you go about calculating something like this? Here E equals Q by 4 pi permittivity of free space R. This is nothing but the area of a sphere is actually 4 pi r square. And the same logic is what we've used here. Now, one more thing that you can actually consider here, the value of Q here, the total amount of electric charge that is actually present here is 4 pi r square multiplied by the charge density. Now, this is how you in fact arrive at the electric field on a uniform spherical shell. Now, why is it that Q has never appeared in the previous 2 concepts? That is, why hasn't it appeared in a thin wire? Why hasn't it appeared in a plane surface? Now, if you consider a sphere is finite in size. If any of you have studied astronomy, you will actually come across this very nice concept wherein it says the universe is an infinitely long plane, because any object, when you start stretching the object beyond a particular limit, the object is no longer having any geometry, it in fact becomes a plane. A sphere, on the other hand, is an object which is finite in size. Because it is finite in size, I can actually find out how many charges are there on an object which is finite in size. In the other 2 cases, let me consider the plane surface here. I can only find the charge density and not really the net charge that is actually there. It's not so easy to find when it comes to the total amount of charges that is there on a plane surface. Unless I say the surface is infinite, but I'm going to consider only this much, which is in fact 3 by 5 centimeters in size. This makes my calculation easier because it's a finite area. But if I say calculate the total amount of charge in an infinite area, I will have to do this calculation for the rest of my life and have generations of my family continue the experiment alongside me. So this is in fact how Gauss law is actually structured. I hope you found my explanation helpful. If I've made any mistakes, do let me know, because this is my first attempt, and if I have made any mistakes, I would love to correct myself and I would love to improve. So do let me know, in fact, if you found this helpful. Thank you for your time. Have a nice day. Bye.